Okay, so at this point, what we're going to do is we're going to describe some other features of a plot. So now, first of all, we've described a, or we've created a descriptor of a curve. But what about if we want to describe some features? So maybe we want to describe some stationary features. So let's think of a plot. Maybe we have something that looks a little bit like this. And we'll call this our y-axis and we'll call this our x-axis. And we're going to draw a curve that looks something like that. And we're going to call that y equals f of x. So we can calculate we can calculate the descriptor of our curve, dy by dx. We could say that that would be f dash x. That's how we describe the curve. But we actually have two features on this curve. We have this point here and this point here. We see a peak and a trough. So what we can do with differentiation is we can actually describe where we can find their location. So how we do this? Well, first of all, is if we call this point A, and we think of what's going to happen here, is our gradient, our local gradient, is explaining how this curve changes. So at this point, this would have to be a positive change, and at this point, it would have to be a negative change. So at some point, as it passes through one point, the gradient would have to change from positive to negative, which would mean that dy by dx would equal 0. And likewise, we'd have a change potentially here where we go from a negative to a positive. So at some point of B, we'd have to say that our change in y over our change in x equals 0. Okay, so that makes quite good sense. So what we'd need to do is we can then say that our change in y over our change in x is 0, and we could actually solve for x. Let's try an example on that. So let's take maybe the curve x cubed minus 4x squared plus 7. We're going to say this is a function of x cubed minus 4x squared plus 7. So if we were just to draw that or sketch it, you could sketch it on the computer, you could sketch it by hand by putting a few numbers, or even some fancy calculators do that. We know that that plot looks something like that. It's not perfect, but it's something like that. It's on the x-axis and the y-axis. So it's in terms of this, be x and y. So first of all, we can take our first differential. So in shorthand for functions, we can just put this little dash here, which would then go to our x cubed, will go to 3x squared. Our 4x would be minus our 4x squared would be that would go to minus 8x, and our 7 would disappear. So what we can now say is, right, well, our f of x, or our dy dx, we want to find the points that they equal 0 here and here. Well, we can say 0 equals 3x squared minus 8x. And if we use our difference of two squares, we could say that x, and we have a x, or a 3x minus 8 in here, and that would equal 0. So our difference of two squares would tell us that x would have to equal 0, or x would have to equal 8 over 3. Okay, so that makes quite perfect sense. So now we can see from this plot here that quite rightly our first point here where it crosses is x equals 0, and this would be x equals 8 over 3. We don't have, if we check that on the calculator, I'm sure we'd find that that's correct. So what we also have is a descriptor of this function here. So that means if we're on a y-axis, we can find that y equals x cubed minus 4x squared plus 7. Therefore, if we were to find out in terms of x what our y value would be, we'd have y equals 0 minus 0 plus 7. So yes, our y value would be around right, which y equal 7. Or if we had 8 over 3, we would say that would be y equals 8 over 3 cubed minus 4, 8 over 3 squared plus 7. And if we were just to bang that into our calculators, we would see that that would equal minus 2 and 13 over 27. And if we look here, that's a negative, so that looks about right for our answer. So we'd have two solutions to our problem. We would say we'd have 2 points, where one of which x equals 0 and y equals 7, and we'd also have x equals 8 over 3 and y equals minus 2 over 13 over 27. So what we might want to do once we've done this is we might want to create a description. So perhaps for this plot, we want to find out if this was a peak or this was a trough, and we wanted to find out if this was a maximum turning point or a minimum turning point. And this will all become clear why we do this in a second. So what we could describe is we have a function which is describing the curve, but what happens if we were to then differentiate again? What would that describe? Well, that would actually describe, we actually have a change in curve at the moment. So we'd look at a change of the curve. So that would actually help us then find the point in which it crosses through zero and help us show if it was positive or negative. So it would show us the change in change that I showed of you if we have a curve like this and we've gone from a negative to a positive or a positive to a negative. By actually taking the second differential, what we can do is find if this is a positive or a negative change, and that will be either a maximum or a minimum turning point. So what we can say is if we took the second differential of d squared x by dx squared, that would have to be if z equal less than or equal to 0 if it was a maximum turning point. So if we had something which was curving up this way, so we had a peak, it would have to be less than 0, which makes sense because we've gone from a positive to a negative. Or if it was a minimum turning point where it was going from a negative to a positive of dx squared by d squared y by dx squared, it would have to be greater than 0, and that would lead to a minimum turning point. And that would describe a trough or something that we might have on a plot, something like this. So let's try sticking some numbers into this and maybe looking at some sort of exam style question, what I might ask. So potentially I might ask you to locate the stationary point on a graph 4x cubed minus 3x squared minus 6x minus 1. Well, with 4x cubed plus 3x squared minus, to make it a bit easier, a positive in here, minus 1. And I want you to find the locations of the stationary points and also the points, or if it's a positive or a minimum, or a maximum or a minimum turning point, if it's a peak or a trough. So what we could say here is, first of all, we would say dy by dx, and we can calculate our first differential, where that would be 12x squared plus 6x minus 6, okay? And what we can do here is we can then solve for 0, where we can say we want to find out the locations of these points, which would be plus 6x minus 6, which we can then factorize to find out, well, we can take a 6 out. We have a positive and a negative. So that would be 6 to x minus 1, x minus 1. If you wanted to, you could use that we're using the difference of two squares rule, or you could use it doing the quadratic rule we calculated last a few weeks ago. And what we would find here, therefore, is we have two answers for x, where we have x equals a half, or x, should be positive, x equals negative 1. So we can do what we've previously done, and we have this first equation where we can stick everything back into the first equation. So we'd say y equals 4 times a half cubed plus 3 times a half squared minus 6 times a half, take minus 1, and we would get the first answer as minus 2 3/4. And likewise, we could do the same with the second value. We say that 4 minus 1 squared plus 3 minus 1, that's a cube, sorry, minus 1 squared minus 6 minus 1 equal minus 1, and we put that in the calculator and we get that equals 4. So we have two values of minus 2 over 3 and minus 4. So if we've answered the first part of the question, where we've shown that we have two values, we have either x and y of our locations. So that would be a half, which would then lead us into y equals minus 2. So x would equal a half, y would equal minus 2 3/4. Or we have a second answer where x would equal negative 1 and y would equal 4. Okay, so now using these numbers, we can find out if these are maximum or minimum turning points. So if we take this Differential we have here, where we have 12x plus 6x minus 6. So we say that is dy by dx, I'll just write it out again, is 12x squared plus 6x minus 6. And we then differentiate that again to get d squared y over dx squared. We'd get something where we'd see 24x plus 6 is our second differential. And what we have here is we actually have two values of x. We have a half and we have a -1. So if we were to plug this half in, first of all, we would get that that would be 24 times a half plus 6. 24 times which equals 18. So that's greater than 1. And as our equation has shown, it's greater. So the first would have to be a minimum turning point. So we'd write that as a minimum. And our second one, if we said that minus 24 times by negative negative 1 times by 24 plus 6, well, that would give us minus 18. So therefore, that would have to be a maximum turning point. So what we've done here is we've now created the full descriptor. We know the locations of our points, and we know if it's a peak or if it's a trough, if it's going up and coming down, or if it's going down and coming up. And that's what differentiations helped us do. So you might think this is a bit abstract and you don't really understand why we're doing it. In the next part of the video, we're actually going to go through some real examples and show how you might be able to use a technique like this in something real in environmental